Greetings. So far we've looked into several methods of solving certain categories of differential equations. But in real-world applications, most differential equations don't fall into those nice, neat categories. Fortunately, also in real-world applications, we usually don't need an exact solution. We just need a numerical approximation that's close enough. And there are lots of numerical approximation methods. One of those methods is Euler's method for approximating solutions of first-order differential equations. Leonhard Euler himself was the most prolific mathematician of the 1700s, possibly most prolific of all time. In fact, the more you study mathematics, the more things you find that are named after Euler. Look him up sometime. He's a very interesting guy. Euler's method in particular, the one we're going to be looking at today, starts with an initial value problem. Assuming you've got some differential equation, y prime equals something about t and y, and an initial value, a t-coordinate and y-coordinate that you know the graph goes through. Euler's method is ultimately very similar to the idea of a direction field, but instead of looking at the entire ty plane, we're just looking at the initial value itself and following from there. So let's say we know the initial value, some location that we know the curve goes through. From that t value and that y value, we can insert those into the differential equation itself and calculate the slope. So at that point, we can know the slope. Let's say the slope is something like this. Any continuous differentiable function is going to look almost linear close up. So let's assume that for a little ways, this function is almost linear, or we can approximate it as a straight line. Follow that straight line for a small distance, and we get to another data point, which we'll call, let's say, t sub 1, y sub 1. And since that's now another ty coordinate pair, we can substitute that into the differential equation and calculate the new slope. Let's say the new slope here is maybe a slight negative, for instance. So it's now going something like that. Follow that linear approximation a little ways, and you get another data point. Let's say t2, y2. Once again, we can substitute those values into the original differential equation, recalculate the slope again, and we have another linear approximation we can follow for some distance. Then we get another data point, t3, y3, and we just continue with this connect the dots approximation until we get to the t value we want, and then we'll find the y value that's associated with it, or at least a close approximation. And of course, this is not going to be the actual shape of the curve. The actual curve maybe looks something more like this. So the further you go, the more inaccurate this becomes. But for values fairly close to the initial condition, this can be a very good approximation. So let's look into how we'd actually find the next data point. Zooming in a bit on this region, let's say you have your initial condition t0, y0. Substitute that into the differential equation, and you've got a slope. Let's say we follow that slope for some distance. In fact, let's say we follow it for a certain amount of distance in the t direction, a certain amount of time, you might say. So let's say you go forward some certain amount of time. We could call that delta t. And you could use a different amount of delta t for each step, but it's often easier if you just use one consistent value. Let's say delta t equals some constant h. H for a horizontal step forward. In the same amount of space there or time, you're going also up some distance, which we would usually call delta y. And that gets you to your next data point, t1, y1. So t1, of course, is just t0 plus delta t. t0 plus h. And then y1, the next y data point, is y0, the original, plus whatever this delta y is. To find that delta y, we can just go back to the original definition of slope. Slope equals rise over run, delta y over delta t. We can fill in y prime for the slope, and this is an approximation, because y prime is the slope of the tangent line, delta y over delta t is technically the slope of the secant line, but they should be pretty close if we're talking about a small interval. So y prime is approximately delta y over delta t. Solve that for delta y, we get delta y is approximately y prime, the slope, times delta t. But delta t is just this constant h. So that's our delta y. This is how far up we're going as we go to the right. We go to the right some constant small distance h. We go up some distance y prime times h. So from your initial conditions and some small time step h and y prime, which you can calculate from the differential equation, you can figure out how far you have to go to get to the next data point. At that next data point, recalculate the slope and continue to the next data point and so on. So you get this sequence of data points that should follow fairly close to the curve. That's the basic idea of the theory behind this. Let's try out an example. Here's a differential equation we've already seen before, y prime equals y over 2 minus t squared over 4. In an earlier video, we drew a direction field of this to sketch out some sample solution curves. Now let's try using a numerical approximation method to get the same sort of results. Using the initial value 0, 2, let's say we want to project that a little bit forward in the t direction, a little bit forward into the future, and figure out what's the y value when t is 2 instead of 0. To use Euler's method on this, we first calculate the slope using 0 for t, 2 for y. Insert that into the original equation, we get y prime equals 2 over 2 minus 0, so that's just 1. That's the slope at this data point. We can project that a little into the future by going forward some t distance and up some y distance based on the idea that y prime is delta y over delta t. So delta y is just y prime times delta t. Of course, we'll need to choose a t step, the h value. And of course, this is a lot of data to keep track of, a lot of information. So it's often useful to organize this into a data table. Let's try drawing out a data table, essentially a spreadsheet by hand, to keep track of all this information. We'll want to keep track of values of t, y, y prime, delta t, and also delta y. So we'll make a column for each of those. T and y start off at just our initial value, 0, 2. We already calculated y prime, plug in 0 for t and 2 for y, we get 1. And now we'll need to choose a delta t value. We want to choose an h step, a horizontal step forward that we can just use for the whole thing. For this one, let's say delta t is an h step of 1 for simplicity. So each step we're going to go one space forward and some amount up or down. So t step is 1, and then to find delta y, once again, we can just say delta y is the slope times the t step. So we'll just multiply these. 1 times 1 is 1. In other words, to get to the next ty values, we take our original t value, add 1, take our original y value, add 1. So 1, 3 should be another point on the graph. Not exactly on the solution curve, but close to it. And then we recalculate, using 1, 3 as our new data point. Substitute 1 for t and 3 for y, and we get 3 over 2 minus 1 squared over 4. 3 halves minus 1 fourth, that's 6 fourths minus 1 fourth, so 5 fourths. Or 1.25. After a few steps, the fractions get pretty messy here, so it's often easier to just use decimals in a calculator. Delta t, we're still using one step forward, one time unit into the future. And then for delta y, again, we multiply y prime times delta t. 1.25 times 1, and we get 1.25. And then again, to get the next t and y values, we take our current t value, add delta t. 1 plus 1 would be 2. And we take our current y value, add our delta y. 3 plus 1.25 would be 4.25. And we could keep going. Substitute 2 for t and 4.25 for y into the differential equation to find the new slope. Still use 1 for delta t, multiply y prime times delta t to get delta y, and add delta t and delta y to our t and y values to get the next t and y values. And you can keep going for as many steps as you need. But in this case, we now have a t coordinate at 2 and a y coordinate that's 4.25. So that's our approximation. When t is 2, y is approximately 4.25. However, this is probably a hideously bad approximation. This is probably nowhere close to the actual value. Because 1 is a pretty big t-step. We're going really far forward and assuming that the solution is a straight line for that entire amount of time. But it's not. The solution curves. How can we get a more accurate solution? Same thing we always do in calculus. Make the interval smaller and smaller and smaller. So let's try repeating this using a smaller interval, a smaller h value. We can still keep the top row, or at least most of it. We'll just need to modify how far we're going forward. Let's say instead of going forward 1 step each time, let's say we only go forward by 0.5, half a second, or whatever the units are. We still have initial conditions 0, 2, and the slope at that point is still 1. But if we only go half a t-value forward, we'll only go a certain smaller distance in the y direction. Slope times h, 1 times 0.5 would be 0.5. Add those to our initial conditions. T plus delta t is our new t-value. Y plus delta y is our new y value. Then we can substitute those into the original differential equation. So y over 2, that's 2.5 over 2, minus t squared over 4, so 0.5 over 4. And we get 1.125, 1 1/8. So that's the new slope. We're still using 0.5 for our h step, our delta t. Once again, multiply y prime times delta t, and we get our delta y. Once again, to get the next t and y values, we just take t and add delta t. 0.5 plus 0.5 is 1. Take our y value, add our delta y value, 3.0625. And then recalculate from there. Use 1 for t, 3.0625 for y. And I'm getting about 1.28125. At some point you just need to round off, but I think we can preserve a little accuracy for now. Delta t is still 0.5. Multiply y prime times delta t again to get our delta y, about 0.64. And then add t plus delta t to get our new t value. Add y plus delta y to get our new y value. And then use the differential equation again. Substitute 1.5 for t, 3.703125 for y. And that's about 1.289. I'll round off a little bit here. Delta t, we're still using 0.5. Multiply y prime times delta t. And that's about 0.6445. One last step, add our delta t to our t value to get our new t value. Add our delta y value to our y value to get our new delta y value, our new y value. So about 4.348. So this is still not all that accurate. 0.5 is still a pretty big time step, but this is at least a good deal more accurate than our original estimate of 4.5. Note though that it took twice as many steps to get there. We were using a t-step that was half as big. That gives us more accuracy, but it also takes twice as many steps to get to the desired t value and the approximation for the y value. So this becomes more and more difficult the more accuracy you want. That is, or not so much difficult, it's the same process. More and more tedious. It takes more and more steps the more accuracy you want. However, this is the same process repeated over and over and over and over again. The same calculation, just with refreshed numbers each time. And what's a very useful tool for doing the same calculation over and over again? A computer. In fact, since we're essentially just doing a spreadsheet by hand anyway, we may as well do the spreadsheet on a computer, using a spreadsheet program such as OpenOffice or Excel. So let's give that a try. Let's see if we can do this same process, but computerize it and make it much faster. So let's try setting up the exact same data table in this spreadsheet program. We'll have to have a t column, a y column, a y prime column, a delta t column, and a delta y column. And the first t value and the first y value we can enter by hand. The initial value coordinates, 0 and t. Everything else, though, we can do by formula. Type equals to start a formula, and we'll want to have y over 2 minus t squared over 4. So we'll click on the y value over 2 minus the t value squared over 4. And that automatically calculates it for us. For delta t, I want to be able to adjust this on the fly. So off to the side, let's just say h equals, and then fill this in over here. Let's say, to start with, let's say 0.5, like we were just using. Then for delta t, we can just type equals, click on that h value. And now anytime we need to, we can adjust that, let's say 0.4, and it'll automatically update. Then delta y, as before, is just y prime times delta t. So we click on, type equals to start a formula, click on the y prime value times delta t value, and we're good to go. Next line, instead of typing in values manually, we can refer to the previous line. So equals the t value from before plus the delta t value. And then for the new y value equals the previous y value plus the delta y value. That's our new t value and y value. And then for the other formulas, we haven't really changed anything. We can just update this by dragging it down. And notice that that automatically updates the formula. This formula was referring to these two squares. This formula is now referring to these two squares, B3 and A3. Same thing here. We can select both of these, drag that down, and that automatically updates. No, it doesn't. Why not? Because this is referring to H3, which is a tile that has no value at all. So we're going to need to modify this. We don't want this value to update. We want delta D to be the same H value, the same 0.5 the whole time. What we can do there is put in some dollar signs here. Specifically, we don't want it to update to H2, H3, H4 as we go down the spreadsheet. So if you just type in a dollar sign right before the 2, now when we drag this down, it's still referring to H2, still referring to that same cell. And you can drag this down as far as you want. Each one is still referring to that same cell. You could also put a dollar sign before H if you wanted to drag that to the right or left and not change which column it's referring to. So that should do it. We now have an entire row that's all formulas, which means we can select this entire row and drag it down as far as we want. In this case, we just cared about up to 2. So 2, about 4.4. And the really nice thing about this is you can now select those columns, T and Y, and hit Chart, select an XY data table. And there is a chart showing the XY values. Of course, just these 5 values isn't all that useful. So let's fill in some more values here. If we just drag this down some more rows, let's say down to here, perhaps up to, let's go one more, get it to 10. So we can now get a much better look at what the graph should look like. XY scatter plot, something like that. Of course, we want more accuracy. So let's see if we can get more accuracy by using a smaller h step. Let's say h equals 0.1. And in this case, to get to 2 requires 20 steps of calculation. But notice we didn't even really need to do anything. With all these formulas filled in, we just type in 0.1 for h, select the last row and drag it down if necessary. But this gives us all the ty values up to 4.53. And it looks like this is actually returning to 4.5-ish. Originally, I thought 4.5 was really inaccurate, and the next step, 4.39 something, would be more accurate. It looks like we're getting back towards a little above 4.5 as we get more and more accurate. And that happens sometimes. Sometimes your first approximation is kind of inaccurate. Your next step might be more inaccurate, but then it gradually gets more accurate as you get further and further out in the sequence. Let's try graphing that. Or actually, let's go out to some more steps. Let's take this down to maybe, how's that gonna work? Let's say up to 11. t and y values up to t equals 11 with a 0.1 h value step. And that gives us a pretty good idea of what this graph should look like. It looks like it starts off at 2, goes up to 5 point something, and it looks like it curves back down, hitting the axis somewhere around 6, and then continues down from there. Maybe we could try even more accurate. Select our t value. Let's try making it 0.01. It's going to take 100 steps just to get from t equals 0 to t equals 1. But we can scroll this down as far as we need to. Drag this down even further. And that is a much closer approximation when t equals 2. Y looks like about 4.559, pretty close to 4.56. So this, I would say, would be a much more accurate approximation because h equals 0.01. We're taking 200 steps to get there. That's remarkably accurate. It's not perfect, but it's a very close approximation. And with the computer, that makes it much faster. And let's see what that looks like on the graph. Maybe we could even take it out to a few more steps. Let's say to look like it crossed the axis around 6. So let's go to about 6 or 7 and see if we can get a better look at the graph. Let's try that. Select these, chart, XY scatter plot. And there we go. This is a much more accurate look at what the curve is going to look like. So that's Euler's method. You can do it by hand, going step by step to get an idea of what's going on. But realistically, if you want a lot of accuracy and a lot of data points, try setting it up as a spreadsheet on a computer. You can get as many data points as you want, as much accuracy as you like by using a very small h step and lots of calculations. And then you can hit scatter plot to get an idea of what the graph looks like. So try that out with some other examples on your own. You can apply this to any first order differential equation as long as you can write it as y prime equals something about t and y, and you have some initial conditions. So try out some examples, and I will see you next time.